Hello everyone. Today is Back to the Future Day. Actually, by the time you watch this, it will probably have been Back to the Future Day because I'm actually recording this at, what time is it? Yeah, 10:49 at night on October 21st, 2015. So, not only has Marty McFly landed in the future, he's probably already gone back to 1985 to discover that Hill Valley's history is screwed up. But anyways, that aside, I thought with Back to the Future Day having been, well, in this case, just happened for you, having been today, I should do a little video on time travel. Reason for this being is I love time travel stuff. That's why I'm a big fan of Back to the Future, Quantum Leap, Doctor Who, all sorts of stuff with time travel, and the book The Time Machine, yeah, which is an excellent book. So if you ever get a chance to read it, really good book. And there's an episode of Sliders that completely rips it off, but okay, maybe they say paying an homage. I don't know. Anyways, so I have kind of collected information about time travel over the years, theories, actual science, all sorts of stuff that I've studied, I guess for lack of a better word, studied. I mean, I don't call it study because it wasn't school, but stuff I've read, science videos I've watched, all sorts of stuff about time travel. So I thought it'd be great to make a video about it. Now, I don't have any citations, unfortunately, for this video. It's not because I haven't learned this stuff, not because it's all a bunch of hogwash that I'm making up. It's because this is stuff I've collected in my head for years, and I really don't know where to link you to. If I come up with, if I find like some sources to link you to that give you the information, I will put them in the comment section, not the comments. Wow, I can't talk today. I'm going to put them in the description of the video below. Hopefully I can find some information, but for now I'm going to post the video and then I'll try to find some sources to link you to. Again, a lot of stuff I know because I've been looking into it for a large portion of my life. So if I don't get sources, by all means, feel free to look up some sources. If I got some stuff wrong, maybe I get some outdated information, feel free to put it in the comments and say, hey, you got this bit wrong, or this is what scientists used to think, but now we know this. So without further ado, let's discuss. So a few things that we can discuss about this. First of all, time travel. Is it possible in real life? And then after that we could say, well, if time travel is possible, if it was possible, what would be the ramifications? What would be the practical outcomes of this? In other words, can I change the past? Can I go to the future and get a gray sports almanac and make myself a millionaire by betting on all sporting events because I have all the outcomes? Yeah. So stuff like that, and if I come up with anything else while I'm talking, I didn't really write this down or script it. I've just kind of been going through it in my head. If I come up with other stuff, we'll go on to that. So, we'll start with the science. So we watch all the science fiction with time travel, and we see it in Back to the Future and Doctor Who, we see it in Terminator. I mean, we see it in all sorts of movies and TV shows and books and comic books and stuff. Is it really possible? Is time travel something that can be done? I mean, obviously no one's done it, no one's developed the technology, but can it be done? The answer to that is yes and no. And you say, how is it yes and no? Couple of reasons. One, excuse me, the laws of physics and relativity as we understand it right now do not expressly or in any way forbid time travel. Whoa! Mind blow, right? Okay, time travel, what? It's possible. Physics allows for it. At our current understanding of physics, of how the universe works, yes, it is possible. Theory of relativity. This is a theory that has to do with space and time. And it's been tested. I mean, it's been tested extensively. So this isn't just some idea Einstein had and we just said, oh yeah, it's right because the math worked. It's actually been tested. It actually implemented in technology. In fact, this technology used every day that depends on general relativity and the fact that it actually works. As best as we can tell so far, the theory of general relativity, it's hit all the check marks on the scientific tests. I mean, so let's talk about what is general relativity. Okay, general relativity has a lot to do with light and time and gravity. Oh, excuse me, I'm sorry. My throat's clogged. So the way we intuitively think about time and space, okay, is different from what general relativity teaches us. In fact, general relativity actually corrects a lot of Newtonian physics. Okay, for example, Newtonian physics tells us, I'm trying to think of something I can compare it to. Okay, that matter has gravitational pull of its own. Okay, and that the mass of the object determines how strong the gravitational pull of it is. So a bigger object has more gravity. So all objects, all matter has an attractive gravitational force, and all matter is gravitationally attracted to other matter. So it would explain, like, say, Jupiter has greater pull of gravity than Earth. Earth has lesser gravity. The Moon has a small pull of gravity, but it has gravity. I mean, even this little flash drive has a gravitational force. Now, for hundreds of years, we thought this was correct. I mean, math worked, but there were problems. There were certain things that Newtonian physics couldn't account for. One is, I believe it's a planetary orbit of Mercury. Newtonian physics could not account for Mercury's rotation because it has kind of a weird orbit, and I'm not really going to get into an explanation of it now. One, because I don't have it all on the top of my head, and two, because it's going to get us sidetracked. But the point is, Newtonian physics couldn't explain that because it didn't really follow Newtonian physics, and for years, physicists and other scientists were trying to figure out, well, why doesn't Mercury's orbit seem to work in Newtonian physics? Well, fast forward to the early 20th century, and here comes Albert Einstein, patent clerk, and he comes up with this theory of general relativity. And here's what it said, okay? Now, Newtonian physics seemed to work. He said, gravity's not really what we think it is. Gravity, he says, is actually a bending or warping of space-time that is caused by matter. Now, in relativity, yes, bigger objects, a bigger planet, a bigger star, whatever, in all matter does affect gravity. They are attracted to each other, but not in the way Newton's theory would have predicted. And Einstein's theory would then be able to accurately explain things like Mercury's orbit, and then there's a whole plethora of other things that it explained that Newtonian physics couldn't explain. But that's an easy one to reference. So think of space as like a big sheet, okay? So think of like a bed sheet. Now, bed sheet's laid out flat, right? You put something on it, it stays where you put it, if it's stretched out flat. Now, imagine you then take a bowling ball or a cannonball or something, and you stick it on that sheet. Now, assume that the sheet is being held up by the end, so it's not just going to the ground, which obviously it would do if it was just floating. So let's say it's being held on all ends, perfectly flat. Someone puts a bowling ball in it. That bowling ball is going to make a depression in the sheet. And what's going to happen is things around it are now going to go into the bowling ball, towards the bowling ball. You're going to say, "Oh, that's gravity." Well, yeah, but it's a visual representation. It's not going to be perfect, but it makes the point: is that space is really kind of like this big sheet. And it's not really a sheet because it's actually, we know it's three-dimensional, but again, we're trying to simplify it here. It's like the sheet, and you put the bowling ball on it. Now, say the bowling ball is Earth or the sun, really any object, but to be really noticeable, we're talking big things like moon, sun, Earth, Jupiter, whatever, makes this depression. And things rotate around it. If you've ever seen, there's something that some, like the March of Dimes has, and I think other charities have, they put in like public places, and it's like this funnel-shaped thing that curves down to a hole, and you put the coin in, and it goes around and around and around and around, and it gradually goes into the hole. That's pretty much what it is, how it works. In fact, we are actually getting closer to the sun. Everything orbiting the sun is actually gradually getting closer. I mean, it'll be way past our lifetime before Earth gets near the sun. In fact, the sun will, I think, will go red giant before we ever get anywhere near there. But things are getting closer and closer to the sun, very, very gradually. And this is because of this kind of depression thing. We're not just going around the sun, we're gradually getting closer to it because of that depression in space-time. Well, anyways, what does this have to do with anything? Well, basically, more importantly, what does this have to do with time travel? Well, time travel also talks, general relativity also talks about how time works. Now, we intuitively probably think, I'm sure unless you know the science already, think, okay, time here and time in space, time on Earth's orbit, time on the sun, time on Mars, time on Jupiter, all flows at a constant rate. Now, this is the intuitive way we think of time. But in fact, time does not move at the same rate everywhere in the universe. Okay? Time is actually affected by gravity, and this is called time dilation. Where there is a greater mass, there's greater mass, so Earth or the sun, that mass actually, the gravity from that caused by that mass actually slows down time. Slows down time. So that means time on, say, a big, huge planet, many times the mass of the Earth, like Jupiter, time is actually moving slower there. In fact, time is actually moving fast, a little bit faster as you in Earth's orbit, as you get away from Earth's center of gravity. And you say, well, how do we know this? How do we know this is right? We know this is right because if you take, let's say you take two clocks and you synchronize them here on Earth. And let's say digital clocks. We'll take all mechanical stuff out of the equation so we can't say, well, lack of Earth's gravity is affecting the gears and the cogs. Take two digital clocks. You synchronize them perfectly on Earth. You leave one on Earth, you take one up to the International Space Station. You leave it up there, I don't know, I'm not sure exactly what the time dilation is, but you leave it up there for a while, however long it would take to make a noticeable difference. You take it back to Earth. That clock will now be ahead of the clock you synchronized it with by at least a few seconds. If you leave it up there long enough, you might actually get to a minute. This is a real thing. We can observe this. This has been observed. In fact, if you have a GPS device, actually any satellite device, but let's take your GPS device. Let's say your GPS device in your car, your cell phone, actually has to mathematically compensate for the difference in time between the satellite and the ground. And I'm not talking about the time it takes for the signal to travel. I'm talking about the actual difference in time. The fact that that satellite is moving through time faster than, and not by a lot because you're still pretty close to Earth, but it is moving faster than your GPS. I think I heard somewhere, I think it was Neil deGrasse Tyson, I heard talk about this. It's something like, 0.075 seconds or something difference in time. It might be small in that. And you say, well, that doesn't seem like much, but think about it this way. If you add that up, if you don't compensate for that, it's going to get farther and farther and farther off. So, yeah, anything. Your cell phone, your satellite TV, basically anything that communicates between orbit and the ground has to compensate for time dilation. Because time on Earth is moving slower than time in space. Or at least orbiting the Earth. Time on Jupiter is moving slower than Earth because Jupiter is much bigger than Earth. So that's one way that time is affected by gravity. That's one thing general relativity says. Okay, so that's one way general relativity affects time. But we're going to get to how this tells us time travel is possible soon. I promise, we're getting to that. But there's another thing that dilates time. Actually, back to the gravity. If you saw Interstellar, you probably heard about this. This is another thing. In Interstellar, they're looking for a new planet to live on because Earth is becoming inhospitable. They go through a wormhole. That's another relativity thing. I'm not going to really get a lot into wormholes because we could go on forever with that. They go through this wormhole to another galaxy. And there's 3 planets that they could potentially habitate. So they're going to check them out. And the weird thing about these planets is they're orbiting a black hole. Is this possible? Actually, yeah, it could happen. But anyways, that's not really that important. These planets are orbiting a black hole. At least one of them is. One of them especially. And they're going to go down on this planet. And before they go down, they have to calculate what's the time dilation. Now remember, this is orbiting a black hole. Black holes, lots of gravity, sucking light, everything else. Well, not sucking, it drops in. Again, another story. On that planet, they calculate, and this is reasonable, that an hour on that planet is 7 years on Earth. That means, let's say an astronaut just had a baby girl born on Earth, had a daughter just born, then goes to this planet through this wormhole. Let's say it doesn't take like years; they get there pretty quickly. And he goes on this planet. Every hour there is 7 years on Earth. So if he stays there 3 hours, if he comes off that planet after 3 hours there and goes back to Earth, his newborn daughter is now 21 years old, and he's only aged a few hours, and that would really happen. This isn't just a movie thing. I mean, this not all the science in Interstellar is perfect, but they get a lot of good stuff right. There's some videos. There's a video again with Neil deGrasse Tyson where he talks about science in Interstellar, and this is something that is they get right. Again, they do take some artistic licenses with other things, but this isn't one. This is relativity. So actually, right there, time travel. That's time travel. Okay. Now, another thing general relativity states is that as objects approach the speed of light, they move slower through time. So that means if you are going near light speeds, you're moving much slower through time than people not moving anywhere near those speeds. Okay? So if you saw Planet of the Apes, the original one, not the remakes, they actually use this. Charlton Heston and the other astronauts are going through space, and they're actually putting these sleep chambers, but they're going at near light speed. So they travel for a long time. We find, of course, at the end of the movie that he's on Earth. But, they're thousands of years in the future by the time they land, but they've barely aged because their craft was going at near light speeds. Now, there's a whole bunch of other things that relativity says about moving at near light speeds, and I'll get into a little of those later. But okay, so that's another thing. As you travel near light speeds, time moves slower. In fact, when you move, period, time moves slower for you. So let's say I'm sitting here in this seat, and my friend leaves the room and walks around the block and comes back. While he's walking around the block, he's moving through time ever so slightly slower than I am. Now, of course, at those speeds, it's insignificant. It's not noticeable. But as small as it is, that friend is moving slower through time and ages just a little bit less in the same amount. And the time he's walking around the block while I'm sitting here. Comes back an hour later. For him, he's been going a little less than an hour. Again, insignificant, unmeasurable, but slower through time. For him, and anyways, a little younger. So, how does this apply to time travel? I've kind of already hinted at it. If we wanted to time travel, it's not going to be like in the movies. It's not going to be like Back to the Future where they just skip over moments of time. It's going to be basically progressing through time slower than the people around you. And, of course, practically speaking, though, there's a lot of issues with this. For example, gravity sucks. It sucks you in. If you went around something with enough gravity to really help you go through time, it'd be very dangerous. It'd be like a black hole or something. I mean, if you ever saw some of the old Star Trek movies, they do this slingshot thing around the sun. I'm not sure how much that would really work, but they're using the sun's gravity. They're employing general relativity, using some Hollywood indulgences, but they whip around the sun to go back in time. So if you wanted to actually use gravity to slow down your time enough so that you could make some significant progress into the future and see the future without aging, you need something really massive. You need, I don't know, you'd probably want like a black hole. I mean, maybe you could find a really massive star, and I can't do the math for this, but I don't think a really massive star would give you enough time dilation again, it has to be something like a black hole. And then you're running the risk of getting sucked in. And where's the nearest black hole several light years from Earth? There's actually a supermassive black hole in the center of the Milky Way galaxy. Yeah, that would give you enough gravity if you don't get sucked in. So we've just ruled out we practically ruled out one method of time travel. Physically speaking, does it succeed? Yes, it is a method. Practically speaking, we really can't do that. It's completely impractical. So now we move on to moving at near light speeds, right? Now, relativity states, and it's been pretty well demonstrated, that matter cannot travel at the speed of light. Nothing can travel at the speed of light. No thing. This is interesting though. Massless particles can travel at light speed. We think of photons and light. There are other massless particles too that move at light speed. There are regions of space that are moving faster than light. And you say, how is that possible? Again, matter can't move at light speed or fast light. Can't move through space. Space itself can move as fast as it wants to. And there are regions of space that are accelerating away from us as the universe expands. They're moving faster than light, which means there are parts of space that are just zooming away from us faster than light. And I'm not going to get into how we know that. That, again, is more science. That's getting into the Hubble sphere and the particle horizon. And that's beyond the scope of this video. And I think you want me to have a lot more research to talk about this and a lot more citation. And I have time to get into. But anyways, near light speed. What about that? Well, first of all, we don't have any vehicles, any means of traveling that fast. We require a massive amount of energy. Now, could we eventually get that energy, find a way to harness that much energy? Possibly. We could use that for interstellar travel and exploring. But general relativity also gives us other issues with moving at near light speeds. One thing that relativity also states is, as you approach light, your mass increases. Whoa, your mass increases? Yes. Mass increases as you get closer to light speed. So think about this. You need so much energy to move, just yourself. Now, and the reason... Okay, yeah, let's get that. You need so much energy to move something. As it gets more mass, you need more energy to propel it. So it's going to get bigger and bigger, because matter has this thing called inertia, which means it resists motion. Matter doesn't want to move. So if you want to move it, you need more energy. So the more mass it gets, the more inertia you have, the more energy you need to propel it. So as you approach light speeds in this amazing craft of the future that you have, your mass is going to increase exponentially as you get closer and closer to light, the speed of light. In fact, if you reach the speed of light, you'd attain infinite mass. So as you get more and more mass, you need more and more fuel, which of course adds more mass. So practically speaking, how in the world would we get to near light speeds? And if we did, we'd be huge. So we got a problem there. Practically speaking, how are we going to get near light speed? We may find ways around this, but I don't think so. That's where we get into things like warp bubbles and stuff. Can that be done? Again, another topic for an entirely different video that I'll probably never do. And a little fun fact about relativity tells us, to something that's moving as fast as at the speed of light, say a photon, there is no time, there is no distance. That means, let's say you have a star that's 4 light years from Earth. A photon travels from that star 4 years, gets to Earth. From the photon's perspective, if it had a perspective, it arrived instantaneously and there was no distance. So if you were traveling at the speed of light, which you can't, but let's dismiss all the other relativistic problems and say you could. And I want to travel from the speed of light from here to a planet on the other end of the galaxy. When I arrived there, I would have experienced no time, no distance. It would have been as if I flipped a switch and boom, materialized there. Is that crazy? That's crazy. But okay, so approaching light speeds to time travel, again, very problematic. I don't know how we do it. Yeah, so we have a lot of practical issues going into the future. Now you're probably saying, hold on, Scott. You've only talked about traveling to the future. What about going to the past? Ooh, there's a tricky thing. Movement, mass, none of that's going to allow you to go to the past. There's one possibility for going to the past. And it may not even be out there. It's called wormholes. You know what a wormhole is? Imagine, you've probably heard this explanation, especially if you're a sci-fi geek. Again, picture space as a sheet of paper. Space isn't a sheet of paper, it's 3 dimensions, but this is what we have to use for an illustration. And you have you have 2 points in space. So you have a space. So you can't see it from here. Oh, go closer to the camera. You have 2 points in space that you want to travel through. You have here and here, and they are light years apart. You're never going to be able to travel through them. But you have a wormhole. A wormhole is a hole in space. Basically, fold up space. I don't think I have the dots perfectly aligned, but whatever. And tunnel right through space to get there. So it's like folding up space, punch a hole, and you're on the other end without having to traverse the distance in between. That is a wormhole. And like black holes, relativity, general relativity predicts the possibility of wormholes. Now, black holes, we've confirmed. We've seen black holes. We've seen the event horizon around black holes. You can't see the black hole because light sucked in and it can't get out. But we've detected the event horizons around black holes. We know there's a supermassive black hole at the center of the Milky Way. There's at least one black hole we've seen in the center of our galaxy. In fact, one black hole we've seen, like regular black hole we've seen in our galaxy. Scientists have actually observed that pretty much every galaxy they've looked at so far has a supermassive black hole at the center. It's like the chewy center of a Tootsie Pop. Anyways, we've seen black holes. We haven't seen wormholes. So the idea behind wormholes is, remember how I said time doesn't move at the same rate in all regions of space? In other words, there could be parts of space where time's moving slower than it is here, or faster. So if you could get a wormhole, somehow you could get a wormhole between here and a point in space that's where time's moving so slow it's in the past, you could go through that wormhole, come out the other end, and you'd be in the past. Of course, it'd be so far away, you wouldn't be able to get back to Earth and see anything, plus Earth would still be in its own time. So it's not really practical. Again, it's not a very practical thing. And another problem with wormholes is, general relativity also predicts it'd be very, very tiny. In fact, incredibly small. They'd appear at random, and they'd be incredibly unstable. In other words, they pop up and collapse in in fractions of a second. In fact, it's very possible that a wormhole could open up right next to you and close, and you'd never know it because it'd be so small and be there for such a short time. Again, they've never been detected. So even if you want to try this wormhole theory, traversing a wormhole, they're too small and they're too unstable. And if you could somehow synthetically, artificially create a wormhole, if you could harness enough power, and that would be an enormous amount of power to actually punch a hole in space from one point to another, and find a way to keep it stable, keep it from collapsing on itself. Unlike in sliders and other science fiction where they're super stable in deep space-time, getting to the other side, you'd be in another region of space, and it may be farther back in time, but you're there, you're not here on Earth, so what's the point? You know what I mean? The goal is to go back in time in your own history on your own planet. Doesn't work. A wormhole from one point to another wouldn't work on Earth because Earth, the time flows relatively consistently all over the planet because it's the same gravity all over the planet. Basically, actually, on the ground it's the same. It gets a little faster as you get up, but not significantly, not enough that it would matter. So yeah, wormhole to go back in time doesn't work. Now, could we someday find out? Like I'm a scientist. Could science someday find out that there are other ways to time travel? Maybe. We don't, science doesn't know everything. They're always discovering new things, finding out old things weren't really as right as they thought they were. Relativity seems pretty solid. There's really no chinks in the armor with that. But could we find other ways to time travel? Maybe. Maybe there's something we don't know about yet. I mean, there's all sorts of stuff going on the quantum level that we don't know what the heck's happening. We don't know how it works. We just know it doesn't make any sense to us, and it doesn't seem to follow the physical laws of the universe on the macroscopic scale that we live on. But right now, yeah, there's no way to skip over, there's no way to time travel other than those ways. And again, it's not like in the movies where you're skipping over time. You are progressing through time. So I can't just jump 30 years in the future like in Back to the Future and just land in 2045. I can't do that. I'd have to travel at near light speeds or orbit a black hole long enough that I would then come out and it would be the future on Earth and I barely aged. So, let's say somehow you overcame all this. Somehow you found a way to time travel like they do in the movies and skip over time. Go to the future, go to the past, and just skip over time. You don't have to traverse through time, you just hop over it. Okay, let's say we found a way to do that. What are the practical implications of time travel? Can I change the past? Can I go to the future and get information about the future? We'll start with not the easier one, but the one that's got a lot more thought into it, is time travel into the past. And there's several theories about this. Okay? So first, let's say we assume time is perfectly linear, cause and effect. If you change the past, it will immediately affect the future. So let's say I want to go back in time and kill Hitler before he rises to power. So excuse me, so that the Holocaust never happens. What happens if I do this? I go back in time and I kill Hitler. Holocaust never happens. Well, if time moves in the way we probably most often think of time, okay, Hitler never rises to power. Holocaust never happens. A lot of history doesn't happen now, but say somehow I still exist in the future. Well, guess what? Holocaust didn't happen now. So why would I go back in time to kill Hitler? It never happened to me. So I don't go back in time. But that means I don't kill Hitler. And if I don't kill Hitler, that means he does rise to power, the Holocaust happens, and I go back in time to kill him. I kill him, now the Holocaust never happened, I don't go back in time. Hitler doesn't die, the Holocaust happens, I go... You see where I'm going with this? It's a loop. I eliminate my reason for going back in time, so I don't go back in time. So what happens? So I go back in time, and that's called the grandfather paradox, which actually stems from the idea of going back in time to kill your grandfather so that you can't be born. Only I'm using a different example because I think we'd rather see Hitler killed than our grandfathers. Unless your grandfather was some psychotic serial killer, but hey, that's your family tree, I don't know. That's a grandfather paradox. That means you try to change history and you get stuck in a time loop. I don't know if that destroys the universe or if it just degrades your timeline or what. But needless to say, if that scenario is reality, then changing history would be a big mistake. Okay, other theory. It's called the many worlds theory. This plays into the whole idea of a multiverse and there being multiple universes. Many worlds theory basically posits that for every outcome of every event, there is a universe where that outcome happened, where that thing was done. So, let's say I cross the street today. In my universe, I crossed the street. Somewhere in the universe, there's now another universe where I didn't cross the street, and things went on from there. Seems a little crazy, right? There's a universe for every possible outcome of every possible action, ever. But this is a many world theory posits. The idea behind this is some kind of cosmic check. Somebody have a cosmic safety check, you know. So nobody screws up the universe and destroys time, time and space. This theory is sort of used in Back to the Future, but not really. They kind of don't do it, but they do. The part where Doc Brown mentions a tangent timeline where Biff gave himself the almanac, and now we have this alternate future. Only in Back to the Future, the future just changes. There is no alternate universe, just an alternate timeline that happens, and the other timeline didn't happen, which would beg the question, then, shouldn't everything Marty and Doc Brown do be eliminated? But let's not overthink the movie. It's a fun movie. In this theory, I go back in time to kill Hitler before the Holocaust ever happened, and I succeed. and a new universe exists where the Holocaust never happened, Hitler never rose to power. Here's an interesting thing about this, though. Many worlds. That means, that would imply that the world where it did happen still exists. So if I think I'm alleviating the suffering by doing this, I'm not. I'm simply creating an alternate universe where that suffering didn't happen. But the universe where the suffering did happen, did happen, still exists. And I didn't really help anyone. I just created an alternate version where things went a little better. Another problem with this theory is, if I do this, and I want to go home, what future do I land in? Do I land in my future? Well, how is that going to work? Because I am now part of this alternate universe. I should end up in the future where it didn't happen. Now, granted, this avoids the paradoxes, but I can't go home to my universe. The universe I go back to, the future I go back to now, is one where the Holocaust didn't happen. Now, this is going to change a lot of historical events. Maybe even I was never born. So I get to the future, I get home, where I think is home, I don't exist. Maybe a lot of things that I know don't exist. Meanwhile, in the future, in the world timeline I'm from, I just disappeared. No one knows what happens to me, but I never returned. That's kind of a lot of things to put your loved ones through, right? You disappeared, you can't get back. Now, from my point of view, yeah, in the many worlds theory, there's no way back home because now you're in this alternate timeline, so you're going to go back to the future of your timeline, unless you find a way to traverse dimensions. You know, if you're Quinn Mallory and you find a way to travel through different dimensions. By the way, Sliders uses the many worlds theory. They don't do time travel, but they go to parallel Earths where history played out differently, and yet somehow everyone still speaks English. Whatever. You know, and the Chandler Hotel is in almost every universe. Anyways, so that's another theory about time travel, the many worlds theory. And again, many problems is you really aren't changing history, you're just creating an alternate universe where the change exists, and again, now I can't go home. Now we're going to get to, out there, I kind of thought of this theory, I'm sure someone out there on the internet is posting this exact same theory, because it's not really rocket science to come up with. But I didn't read this theory, I thought up this theory, and again, it's probably out there. Someone probably thought of up before me. I'm not that brilliant, I'm the first one to come up with this theory that you can't change history at all. If you go back in time, you were always part of events. That means, if some point in the future, I discover time travel comes into existence, and I use it, and I come back in time to this very moment, and pop out in my kitchen out there, and start cooking waffles, that means right now, at this very moment, future me is in that kitchen cooking waffles. Time doesn't get changed, I'm out there now. And seeing as I don't smell any waffles, and the lights are out, looks like I'm not doing any time traveling, at least not to here and now. In fact, I'm going to say this right now. If time travel ever happens and I get it, I'm going to come back in time to this very moment and make waffles in my kitchen. And now we wait. Okay, either I forgot about it or it doesn't happen. So much for that. But that's my theory, is that you can't change the past. You go back in time, you try to change things, and you can't because you were always part of the event. So if I'm going to go back in time to try to kill Hitler at some point in my life, I can already safely say I failed. Because I was always back there, I always tried, and obviously I did not succeed because Hitler was not killed before he rose to power. So, that's my theory. So if time travel like that ever happens, and my theory is correct, you can't change history, you're always there. But, my theory also allows for the safest time travel, because that means you can go back in time as an observer, you can witness historical events, and you won't change a thing because you were always there. I can go back and watch the Revolutionary War in a garden chair, in a lawn chair, sit back and watch the redcoats and the colonists fight it out with their muskets, and, you know, it's cool. I'm not going to affect history in the slightest because I've always been there watching it. And again, that's assuming that you could time travel like Ken in the movies, which right now does not look possible. So those are my theories. And actually, one more theory. This is what Einstein posited, and he was a really smart guy, so maybe he was right. Whatever you do in the past, no paradoxes would occur, somehow the timeline would correct itself. Which almost implies that the universe and space-time are sentient beings is a sentient being that can kind of make sure no paradoxes happen. I don't know. But those are the theories that are out there. So if you've been wondering about time travel, There's some science behind it, and there's some theories of what would happen if time travel happened. Now, don't let this ruin your movies. You know, they're fun. It's fantasy. It's supposed to be fun. We can watch the Back to the Future and ignore all the glaring temporal paradoxes and say, it's just a movie, it's a what if, it's having fun. Let's not get all bent out of shape about this. So I hope that was informative to you. I can't think of anything else to talk about. Okay, slightly awkward. I kind of forgot to talk about repercussions of time travel to the future. My bad. So that means this video is getting up even further past Back to the Future Day than I had planned, but it's okay. Sake of completion, let's talk about time travel to the future. We talked about time travel to the past, what could possibly happen there, and all the theories. So now we go to time travel to the future. Now, Back to the Future, Marty McFly goes to 2015, where he buys the Gray Sports Almanac with all the outcomes of sporting events from, 1950 to 2000. And of course, Doc Brown won't let him take it back, but old Biff, he finds the almanac. Well, of course, he didn't have to really find it. He could have gone to any store and bought it, but he finds out that Doc Brown made a time machine and, gets the same idea. Oh, I'll take this book back. I mean, he saw the book in the trash. He saw Marty throw it out, and he said, I'll do that. So he goes back in time and, of course, gives his younger self the sports almanac, which completely screws up the timeline. I don't know how he even got back to his original timeline if he screwed it up, but again, we'll make some allowances because it's a movie and it's fantasy. But so is what we're talking about as far as jumping over time. So, Anyways, what about real life? Again, this is all theory. Well, and I don't want to abuse the word theory because theory in science means a very different thing than it does in layman's terms. So, if you're a very sciencey person, please don't take me the wrong way saying theory. I realize saying just a theory doesn't make a lot of sense to a scientist, but, anyways, I'll say a hypothesis. How about that? I say a hypothesis. This is all hypotheses. Because we have no way of testing them, because we can't time travel. We can't jump over time to the future or to the past or anything. So I go to the future and I get, let's say I do the same thing. I get some sports almanac so I can make myself wealthy. And I go back in time, to my own time. And I want to make myself rich. So, let's see. First of all, in time travel to the past, I talked about the grandfather paradox. How does that apply to time travel to the future? Now you're saying, well, I'm going to the future, I haven't been there yet. So I'm not trying to change the future, I'm trying to change the present. Yes, the present for you, but the past for the future that you just went to. So, how does this play out with the grandfather paradox? And for me, I've put a lot of thought into this, probably more than a normal, healthy human being who's not a scientist should be putting into it, but that's okay. Okay, it's probably not okay, but I'm not going to beat myself up over it. Okay, I'm here, and I jump to the future. And I see that my life in the future is miserable, that I have, that I'm bankrupt or whatever. I want to fix my future life, and I think money's a solution. Money is not the solution to all life's problems, but let's say I'm just that materialistic, and I think that's true. So I decide to get a sports almanac and go back in time and place bets and make myself a millionaire just like Biff Tannen did. Here's a problem. While it is the future from where I came from, I went to the future and I saw that my future is lousy, right? Okay? Now, by going back in time and making those bets, I'm going to change it. Maybe not for the better, but I'm going to change that future. That future will no longer be there to influence me if I go there, right? So, I change that future. Now, that future is no longer there for me to have seen. This gets kind of complicated because, again, we're talking about time travel to the future. Can the future change the past like this? How do I explain this in a way that makes sense? Because I change it because of what I saw, by changing my timeline, I'm not changing what I could see, which means that future is no longer there for me to see. This is, of course, not using the many worlds theory. This is using, changes here affect the future in the real timeline. This is using the grandfather paradox setup. So by changing my future, I now don't have that future to see. Because while it's a future, my visit there is my past. Even though it's the future of everyone else, because I was there. My personal timeline kind of makes this weird loop where I jump to the future of everyone else and then to the past. But it's still my timeline. So for me, it is the past. So yeah, I've changed what I saw in my past in visiting the future. A little complicated, but not really that complicated. But yeah, you just change something. Now, let's take this at another angle. Let's say I haven't seen the future, but I've decided I want to get that almanac and make a lot of money. So I go to the future, and I grab the almanac, I come back. Never encountered my life. I don't really know what my future life's going to look like. Well, now, all the reason for getting the almanac was just I wanted to get rich. Make myself rich. I had not changed my reason for going. Therefore, getting myself rich would not cause a paradox because it wouldn't eliminate my reason for going there. You see what I'm saying? It will change my future, or will it? Or will it? Now, under the grandfather paradox scenario, yeah, I changed my future, and I don't have the paradox, I didn't see it. But let's go back to my theory, where you can't really change the past. You can't really change the past, all right? I go to the future. Now, I come back, right? Well, that past I come back to with the almanac is the past of the future I went to. So that future's already there, which raises a whole other set of questions or issues that I'm going to get into. That future is already there, which means how can I change it? It's there. I can't change the past. This is the past of that future. Therefore, when I went to that future, I was already rich from the almanac. Okay, and here is interesting problem though. If there is a future for me to go to, right? And I'm kind of gonna let this sink in. It's a little kind of surreal to think about. If there's already a future for me to go to, that means that by jumping over history, not progressing through it by traveling at near light speeds or whatever, but by using Back to the Future technology and just jumping over time, that means that future is already there. Because remember, I skipped over some time. That means that time was already there, which means that history was already there. If that future history was already there, that means before I left it was there, which means, or would imply, that the whole of time is predetermined. Because there's a future for me to go to. See, if the future's already there for me to go to, things have already, with stuff having happened, the outcome of where I am in my actual present, or what should be my present naturally, then the future's already written. Which means all of history is predetermined and we have no free will. We can't make any decisions. Whatever happens has to happen. It can't happen any other way because it's already been predetermined. Even me sitting here having this discussion with you on the other end of the camera who can't talk back to me and I can't see you. Even this had to happen. It was going to happen. It was always going to happen. It always will have happened. And whatever's going to happen tomorrow is predetermined. So that raised some issues. That's philosophical. That's a difficult thing to come to terms with. Which is what's interesting when Back to the Future. Because at the end of the third one, right, Jennifer says to Doc Brown, "Oh, the facts is erased. What does that mean?" And Doc Brown means, "It means your future hasn't been written yet. Nobody has." And it's like, wait a minute. If nobody's future's been written yet, then how could you have gone to the future and seen that Marty's kid was messed up? I mean, if it hasn't been written yet, you shouldn't have been able to go there. You shouldn't have been able to come back and say to Marty, "We've got to do something about your kids." There's a big contradiction there. If you can go to the future by jumping over time, then that means the future's already been written. which would also mean that everything's predetermined, which means that we go back to my theory that you can't go back in time and change the past. Now, do I think everything's predetermined? No, I think we do have free will. But, again, in this scenario where I can go to the future by jumping over time, there's a future there for me to go to. Things have been predetermined. Of course, if I can go to the past from my future, would that, and that past is that, wouldn't that imply that in that time the future was already predetermined because I came back? Because remember, I go back there to all those people. It's the present to them when I go back in time. And it's just an interesting thing. If the past is there going, if I can go to the past and it's going on, then does that mean that the future was going on while that time was there? Does that mean that everything predetermined? It's really, time travel to the future is probably a bigger quandary than to the past because it raises all these questions. I can't think of the word I want to use for it. That it's not philosophical. I can't think of the word I want to use for it. It'll probably come to me an hour or two after I turn off this camera and I'm trying to go to sleep, and all of a sudden it'll just pop into my head and whatever. So yeah, that would be time travel to the future. That is, I don't know. I'd be afraid to try going to the future and finding out. Sorry, but then again, if it's not predetermined, that means if it's not predetermined, if we have free will, if everything we do isn't set in stone, that it has to be what we do, then I would say then there's no future to go to. If I time travel to the future using Back to the Future technology, I couldn't get there because it hasn't happened yet. I don't know if that's a scientific way to look at it, but that's the way it seems to work in my head. But then again, if science has taught us anything, it's that if it's intuitive, it's probably wrong, especially when it comes to relativity. Yeah, so I'm probably totally wrong about that. And then you watch movies like Interstellar where they talk about the fifth dimension, and that just makes it look even more like things are predetermined. Because again, that's an actual scientific concept that maybe there's this fifth dimension. You have our dimension, the three spatial dimensions of the time dimension. The fifth dimension would be actually being able to step outside of time and look at time in front of you and be able to see all of time at once. Which would mean, again, well, if I can see all of time at once, past, present, and future, then it's all predetermined. And then I wonder, well, when I'm in the fifth dimension, if I'm not in time, what is this progression of stuff where I'm looking around? What is that? If I'm outside of time, that's a whole thing that really I've only just begun thinking about fifth dimension, and again, that's even if there is a fifth dimension, which honestly we don't know because we have no access to it. If it's there, we have no way to test for it. But anyways, I hope I presented some interesting facts. You can think about it and kind of get a better handle on real-world time travel, which seems incredibly impractical. And I know I mentioned warp bubbles. Again, that's another science. I talked about that when I was talking about moving through light speeds. In short, a warp bubble, though, just to clarify, when you see people in Star Trek and they're going at warp 9, warp 7, whatever, and you go, well, aren't they traveling faster than light? Well, the theory is that in the show, they're traveling through something called subspace, I believe, which would put them outside of space, which would allow them to travel faster than light. Real scientists theorize a warp bubble a little differently. A way of using power, energy, and you have to have a lot of it, to bend, to stretch and contract space so that you move, so that space propels your vehicle, your spaceship, through the universe, and so the space is moving and not the vehicle itself, not the ship itself. You have a bubble and you expand in the back, you expand in one end and you contract it, and you basically have a region of space that you're traveling in, that the space is moving and not the ship itself. So therefore you get around that little caveat of I can't travel, you can't travel, no objects can travel through space at light speed or faster than light. Well, now no object is space, you're actually making space itself move. Not sure how that would work, but it would require enormous amounts of energy. So just to clarify that, it doesn't really have anything to do with time travel, but I figured since I mentioned Star Trek and how they slingshot around the sun, I'd explain why they couldn't just use warp speed, why warp speed didn't send them through time. That's why. And again, you really couldn't go to the past using that slingshot maneuver. You'd actually have to go to the future because it would slow down your time, not speed it up. So hope you enjoyed the little video, and I will hopefully have this posted. Hopefully you're watching this on like Thursday. I'm not going to be able to post it now, it's too late. So I hope you enjoy it.